All right, good morning. Happy Tuesday. So this lecture is going to be part one of sound lectures. And then we're doing two more parts and then we're done with this unit. So we have nature of sound. So sound is energy and it's something that exists whether or not you can hear it. So that's kind of referring to the whole idea that humans have a specific range in which we can hear. And there are sounds that exist above and below that we cannot hear, but that doesn't make them not sounds. So sounds is something that we think of as something we can hear, but it's not necessarily always going to be the case. The origin of sound. It says most sounds are produced by vibrations, and there's a lot of examples. So a violin, piano, guitar, the strings vibrate, and the saxophone, the reed vibrates, and the flute, the air vibrates. For your voice, your vocal cords vibrate, and then they vibrate the air in your throat and then the air outside of your body, and then pass it along to the next person to hear it. So just a quick content check. How are sound waves produced? Origins of sound continued. So the original vibration stimulates a vibration of something larger. So for example, the sounding board of an instrument, the air column of an instrument, the throat and mouth of you when you're singing or talking. And then it sends a disturbance through the surrounding medium, which is usually air, in the form of longitudinal sound waves. So sound waves are longitudinal, that's a key point. And usually through air. That's not the only thing they travel through. They travel through everything, but primarily air is what we're talking about here. And those three questions just pertain to this section, so just reread it if you need to. Okay, so sound waves have a frequency, which we're familiar with the frequency. A frequency is seconds per, or cycles per second. So how many times does the crest pass per second or the pendulum swing per second? That is your frequency. Now in sound, frequency is actually the pitch or the note of the sound. And it seems like that would be absolute, but it actually isn't. It's a bit subjective. And so the frequency of the sound that you hear does vary, and therefore, it is called pitch. Just like the note, like middle C or something. A person who is young, very young, can hear from 20 hertz, which is a frequency, to 20,000 hertz. As we grow older, the limits of hearing shrink, especially on the high end. And so this is a YouTube video that does a hearing test. You have to wear headphones when you do this. And when it starts to, it's going to go, the frequency right here is going to go down, I believe. And then whenever you can hear it, your hearing age. When I did this, I got it almost exactly at my age, give or take. It goes pretty fast, so it's kind of hard to catch it. Excuse me. So you may need to do it a few times to really get it right on your approximate age. There are factors that affect this. So if you listen to loud music in your ears a lot, like with headphones or earbuds, it'll increase the age of your ears, so to speak. It'll actually kind of dampen the high end of your range. So it wouldn't be unheard of for you to have the hearing of like a 20 or 25-year-old when you're 16 as a result of just damage to your ears. So I want you to test it, and then you're going to tell me how old was your hearing? What did you figure out? There are many other videos on YouTube that do hearing tests. So if this one is, you're like, let's see if there's something better, feel free to look around and find a different one, and just let me know what you're hearing. How old is your hearing right there? The very first slide says sound is something, an energy that exists whether or not you hear it or not. And this is like the official term. So infrasonic is something that the frequency is too low for human hearing, so less than 20 hertz. There are many animals that communicate at this level where we can't hear it, it's too low. And I want you to go look it up and find an example of an animal that uses infrasonic. So in other words, below the hearing range of humans. Now that doesn't make it not sound, right? It just means that we can't hear it. A lot of things in the universe are labeled based on what we can see. For example, visible light. We call it visible light because that's what we can see. It's not necessarily what other animals can see. Same for sound. So the sound range that we can hear, we kind of consider that audible, even though there are other animals that can hear above and below that range. There are also animals that hear above 20,000 hertz, so too high for us to hear. And I want you to also find an animal that uses that a range above 20,000 for this question here. Humans cannot hear infrasonic or ultrasonic sound because it is above or below our hearing range. Sound in air. Sound waves are vibrations made of compressions and refractions. They are longitudinal, they require a medium, and they travel through solids, liquids, and gases. So in this picture, it's kind of trying to demonstrate what a compression and a refraction is. So in this first image, it's showing someone pushing the window open or pushing the flap open, whatever it is. And when he pushes it open, it pushes the air inside and causes the air to go out the window. And you can see the curtain outside the window. When he closes it, he essentially creates a less dense air and pulls some of the air out with this flap, causing the air to suck in and pull the curtain in. It's kind of hard to interpret what they're trying to talk about in this picture, but this is where they're pushing the air closer together, and this is where they're pulling the air further apart, and that's what that's trying to demonstrate. Check all that are true about sound waves. So read through this again, read through this, and see if you can figure out which ones are true. Click all that are true. All right, compressions and refractions. So here's a visual of that. So compressions are when the molecules are really close together, like more than normal. And refractions is when they're more spaced out, more than normal. And so the question here is just like how many compressions are in this image and how many refractions are in this image. You're not going to count this refraction that's on the very, very end here that you can only see a little bit of it. So that one's not counted, but the rest of them are. All right, a sound from a speaker. So a speaker has a membrane, like paper cone is what it's saying here, and that vibrates, it pushes and pulls the air, creating a longitudinal wave, which is sound to us, and it travels through the air, it reaches our ears, it vibrates our eardrums, and then we hear the sound. So how does the speaker get from the sound from itself to your ear? Read through that again if you need to. Okay, so remember I said before that the medium is usually air? Well, kind of, but any surface, substance can transmit sound, solid, liquid, glass, or even plasma. When the atoms are closer together, they transmit energy faster. So imagine standing 2 feet apart in a row, like let's say 10 people standing 2 feet apart, all lined up, and they have to pass a volleyball. They're going to be able to pass it pretty fast compared to if I had everyone stand 10 feet apart and you had to walk the ball to the next person. So instead of like you can't throw it or anything, you have to actually pass it. So each person would have to walk to the next person to hand it off. It would take a lot longer than if you were standing only 2 feet apart and you could just turn and pass the ball. And so that's the idea behind why sound travels faster in liquids and then even faster in solids, because the molecules are densely packed, and so the energy transfers from one to the other much more quickly. There's an old, I remember seeing this in old Westerns, that they would put their ear to the ground to hear if there were horses coming, because the sound of the horses' hoofs hitting the ground would travel through the ground much faster than through the air. So before they could even hear the horses coming, they could hear them if they put their ear to the ground. I've also seen this done with train tracks. So before you can hear the train coming in the air, you can hear the train coming on the track if you put your ear to the track, because sound travels 15 times faster in steel, so like the train tracks, than it does in air. So you're going to get 15 times more warning than if you were just listening for the train coming. So that's another one you can do is put your ear on a table and have someone just kind of gently tap the other end of the table, versus, and then sit up, have them do the same type of tapping and like listen to the volume of it. Then put your ear back down on the table and tap again. Also, like you may experience this if you swim. If you're underwater, you can hear like little tiny things clanging that you wouldn't really hear if you were outside of the water. Like the little flap that keeps the debris out, you can't really hear it. You can hear it, but I mean, it's not very loud when you're out of the water. But when you're under the water, you can hear it going clink, 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 because the sound is traveling much faster under the water, and therefore you're getting a larger volume in that situation. How fast does sound travel in air? So it does depend on conditions. Dry air that's 0 degrees Celsius is 330 meters per second. And depending on the temperature, it can vary. So as the temperature rises, the speed rises by 0.6. So there's actually a formula that you use, and you go 330 plus or minus 0.6 per degree, and it gives you the exact speed in that air temperature. However, we're just going to pretend that everything is at those specific conditions. We're not going to do the calculation and adjust by 0.6. So how far does sound travel in 1 second on a dry day, so dry air, and a temperature of 0 degrees Celsius, 0 degrees Celsius? The answer would be 330. And the next question, you watch a person chopping wood and note that after the last chop, you hear 1 second later. How far away is the chopper? So exactly 1 second would be exactly 330 meters. And over here, I just have assumed the temperature is 0 degrees and the air is dry, just so you know that we're following these conditions here. So we're assuming that this is the speed, 330 meters per second. And then for the last question, same thing. You hear thunder 2 seconds after you see a lightning flash. How far away is the lightning? So light travels crazy fast compared to sound. And so when you see lightning, then you count seconds. That tells you approximately how far away the lightning is. So 2 seconds, every second it travels 300 meters per second. So in 2 seconds, it would be double that. So 330 times 2. Okay, so this concludes section sound part 1. Complete and submit the Go formative. Do not forget to do the Edpuzzle as well. And that's the end.